Hi, we are Team Gorillas Cows, and we're going to be tackling problem B today. My name is Kevin, and I'm from New York University.
I'm Srinivas. I'm also from NYU.
And I'm Anatulya, and I'm from UC Riverside.
And this will be our presentation on the dynamic bounding confidence model with mood.
So we're modeling opinion dynamics in a population using a bounded confidence model. Each node or agent contains a continuous opinion within the boundary of 0 to 1 and interacts with its neighbors using a confidence threshold. We aim to simulate how varying opinions evolve through these interactions, especially by observing how initial opinions spread and converge over time. On the next slide, you will see each node's initial randomly assigned opinions organized in an Erdos-Renyi graph before any interactions occur.
Okay, so on every time step, we do two operations. The first operation is updating the opinions between the nodes. So what we do is we select k edges uniformly at random and without replacement. And if these two nodes are similar enough in opinion, they will essentially compromise their opinion. This is modeling where if I interact with another person with an opinion close enough to me, I'll kind of compromise my viewpoint to align with theirs. And basically, this is the mathematical equation. So each node is updated to converge to kind of the same point, and you're adding kind of the distance between the opinions. And it's also scaled by a factor of alpha, which is between 0 and 0.5. And you can think of this as influencing the size of the opinion changes, or you can think of it as it's influencing the speed of the convergence, essentially making it faster to converge to one opinion or multiple, as we'll see later. We only compromise two nodes if the distance between their opinion is less than C, which is the confidence bound. The second operation we'll be doing is adaptive rewiring. So we will select M edges or connections uniformly at random without replacement every time step. And we will detach this connection, pick either node in the edge, right, to rewire. And we'll basically compare that selected node with all the other nodes in the network, and we'll create a probability distribution where we'll randomly pick a second node, but it's weighted based on their difference in opinion. So you'll most likely get paired with a node that is closer to you in opinion. And this is essentially trying to model how we kind of want to choose to be in communities where people have the same opinion as us. So we kind of rewire ourselves. And one important thing to note is that, like the confidence bound is kind of similar, is that the change in the difference in opinion has to be greater than this beta value in order to start rewiring. And this is just a visual. I'll go through it quick. So we have two nodes. They're connected to each other. This is an edge. And the edge is disconnected. And then one of the nodes is picked. It has equal probability. In this case, I is picked. And I will be compared to every other node in the network. And then one of the nodes will get randomly picked, except it's weighted, as I said before, based on their difference in opinion.
So now we're going to be interpreting some of these parameters. So as we've modeled every single confidence bound possibility, we've noticed that from 0 to around 0.6, there's a varying amount of clusters. And at around 0.26, that's when it converges to one cluster. So essentially, having a confidence bound of over 0.26 means that the entire population will converge to one opinion or consensus. And this can be very important later on when we model just how mood can affect or what type of messaging can affect the population's opinions.
And one thing to recognize, can you go back to the back slide, is that C, again, represents the open-mindedness between the nodes, and beta represents the threshold for disconnection, or basically how much can I take when I interact with someone before I need to leave and go rewire myself.
So these are some of the results. A confidence bound from 0.01 to 0.12 would give a highly fragmented opinion cluster or opinion graph, where you can see the red, blue, and yellow are highly different in little clusters. And then now there's only two clusters, which is a polarized group and then a consensus where everyone is in under one opinion. So now how can we add mood to this? How can the efficacy of a node affect the opinions? So through the study linked in the problem, a negative mood would trigger item-specific processing, whereas a positive mood would trigger relational processing. And these differ how negative moods would focus on the message elements without connecting to the larger context. So essentially, this is just negative moods are more open to other kind of opinions, whereas positive moods only look for units according to similarity, meaning they want opinions that are similar to them. You can kind of think about this as a person who's having a really, really good day. They wouldn't really want to be around people who are kind of sad and gloomy, whereas someone who's sad and gloomy might seek out a really positive place. So, and how we're going to implement this into our model, similar to how we generated each opinion for each node will have a similar mood value, which is a continuous value from 0 to 1. And as a mood closer to 0, that means a negative mood, whereas a mood closer to 1 would mean a positive mood. And these moods and these kind of nodes will now have a kind of a second layer of interaction, where how does a negative node and another negative node interact versus a negative and a positive, or a positive and a positive. This is what we're going to be going to right now. If mood I and mood J, let's say that's two nodes we just picked, whereas before we rewired and kind of went through all that. Now, if both of these nodes, now with the new understanding that negative moods will make them more susceptible to seek out opinions that are not close to them. So that means we will create our beta to be greater than before and our C to be greater as well, meaning that two negative nodes will kind of want to look for more opinions that are not similar to them. Whereas two positive nodes would seek a confidence bound and a beta that is lower, meaning that they really, really want to stay near their opinion and not find other people kind of unsimilar to them. And this is kind of the special case. What if one node is positive mood and another node is negative? This is where we'll update our confidence updater. But now we'll introduce a parameter Z. So Z would make each positive node change less, whereas a negative node would change more. And you kind of see this how a negative node was really open to change, whereas a positive node is really strict to change. So that's why the negative node would kind of get a boost from Z, whereas a positive node would kind of lower from Z. And we set Z as 0.05. This is kind of a limitation of our model where we don't really have the tools and data to test just exactly how it is, how Z should be, how these kind of opinion and mood processes change. But we set 0.05 as a placeholder for now. And this is a limitation and kind of something we hope in the future we can change. And now we're going to interpret this graph where before we had a 0.26 flatten out rate, but now there's a 0.335 flatten out. So this pretty much means as we add this kind of human quality of mood, this more dynamic variable, now populations need a greater confidence bound. Kind of they need to be more open-minded in order to form a consensus. And this is kind of the effect of mood. How mood will kind of pull them away. So as kind of your confidence bound, whereas before confidence bound needed to be 0.26 to form a consensus, now it's greater. So now kind of clusters will be further and further away, where before it was kind of closer. Now it's a little bit farther away, but then we still need a 0.3 plus confidence bound to form a consensus. So
with the addition of mood, populations need larger confidence bounds, meaning we must be more open-minded and accepting of different people's opinions. Negative messaging can push for a quicker consensus, but we should question if what consensus is always the goal. Our model shows that when the confidence interval is above 0.3, consensus forms easily. And persuasive messaging, especially when negative, can unify opinions rapidly. On the other hand, positive messaging fosters alignment by emphasizing shared values, promoting healthier discussions, for instance. However, society requires both fragmentation and consensus. So for diverse perspectives, they're essential for meaningful discourse, while agreement is necessary for collective action. Disagreement fuels innovation and also prevents stagnation. So balance is key. As politics grows more polarized, this model underscores the need for open-mindedness and the value of engaging with differing opinions. From an economic and health standpoint, balanced messaging helps maintain societal resilience by ensuring a space for both unity and diversity of thought.
Thank you so much for listening. This was Team The Realest Cows. Have a great day.